Start with the real numbers. One real number lives on a line. Left and right is enough. But a complex number needs two real numbers at once. That's why one line isn't enough. A complex number is written as z equals x plus iy. Here, x is the real part and y is the imaginary part. The symbol I is defined by the rule I squared equals -1. That rule isn't mystical, it's just a definition that lets us keep track of the second number. So, a complex number is really a pair of real numbers, x and y, written compactly. To represent two numbers geometrically, we use two axes. This gives the Argand plane. The horizontal axis is the real axis, the vertical axis is the imaginary axis. The complex number x plus iy is plotted at the point with coordinates x, y. For example, z equals 3 plus 2i means move 3 units to the right and 2 units up. That point represents the complex number. You can think of this point in two ways. As a point, it is a location. As a vector, it is an arrow from the origin to that point. Both views matter. Points are useful for loci. Vectors are useful for adding and subtracting. From the picture, two key ideas appear immediately. The modulus of z, written vertical bars z vertical bars, is the distance from the origin to the point. Using Pythagoras, the modulus is the square root of x squared plus y squared. The argument of z is the angle the line from the origin makes with the positive real axis, measured anti-clockwise. So distance gives modulus and direction gives argument. This leads to two ways to describe the same complex number. Rectangular form tells you how far right and how far up, x plus iy. Polar form tells you how far and in which direction, r times cosine theta plus I times sine theta, where r is the modulus and theta is the argument. Using Euler's formula, this can be written as r times e to the power I theta. It's the same point, just described differently. Now look at operations. Addition of complex numbers is simple on the Argand plane. Add real parts and add imaginary parts. Geometrically, this is vector addition. You place one arrow head to tail with the other. Adding complex numbers means adding movements. Multiplication is the crucial idea. In polar form, if you multiply two complex numbers, you multiply their moduli and add their arguments. Geometrically, multiplication means scaling and rotating. This explains why multiplying by I is special. The number I has modulus 1 and argument 90 degrees. Multiplying any complex number by I rotates it 90 degrees counterclockwise about the origin. That rotation is exactly what the algebra produces. Division reverses this process. You divide moduli and subtract arguments. It's inverse scaling and inverse rotation. The complex conjugate also has a clear picture. The conjugate of x plus iy is x minus iy. On the Argand plane, this reflects the point across the real axis. Multiplying a complex number by its conjugate gives the square of the modulus. Finally, the Argand plane makes loci easy to see. The equation vertical bars z minus a equals r means all points a distance r from a fixed point a. That is a circle. Vertical bars z minus a is less than r is the inside of that circle. The equation vertical bars z minus a equals vertical bars z minus b is the perpendicular bisector of the segment joining a and b. An argument equation describes a ray or a sector. The Argand plane turns complex numbers into geometry. Real parts become horizontal positions, imaginary parts become vertical positions, modulus becomes distance, argument becomes angle, addition becomes translation, and multiplication becomes rotation with scaling. That picture is the point of the Argand plane.